I believe you're well. Teacher Mercy here again with a very interesting lesson on electrochemistry. Hope you're going to enjoy. Welcome. Now, electrochemistry can be defined as the study of the effects of electricity on a substance and how chemical reactions produce electricity. So, we are going to deal with two aspects of this topic. One is the study of the effects of electricity on a substance. What happens when you pass electricity on a substance? It can be a compound, it can be an element, and so on. Then we shall also look at the chemical reactions that are produced by electricity. How chemical reactions are produced by electricity, and we shall also go into details about such chemical reactions. Therefore, in attempting to discuss all that, we shall deal mainly with reduction and oxidation. Now, reduction and oxidation means redox reactions. Reactions whereby reduction and oxidation happen at the same time or simultaneously. Secondly, we shall deal with the electrochemical cell, also called the voltaic cell. Then finally, we shall discuss electrolysis, whereby we shall look at the electrolytic cell. Now let's begin with reduction and oxidation reactions. These reactions I've just told you, they are called redox reactions, and they happen when both reduction and oxidation happen simultaneously. Now, before we go to details about redox reactions, we first need to know the definition for reduction and also oxidation. Differences between oxidation and reduction. Now, several definitions can be gotten out of reduction. For example, reduction can be defined as the loss of oxygen from a substance. An example is when you react copper 2 oxide with a more reactive metal like iron. Iron will reduce copper 2 oxide by taking away the oxygen from it, and the product will be iron 2 oxide plus copper. So there is loss of oxygen in that reaction, because the more reactive metal, which is iron, takes up the oxygen from copper 2 oxide. So copper 2 oxide has been reduced. Now, reduction can also be defined as the gain of electrons. When a substance gains electrons and becomes more negative, that is also a reduction. Then, it can also be defined as the addition of hydrogen. When you add hydrogen to a substance, you are also reducing it. That is also called reduction. And finally, reduction can be defined as a decrease in the oxidation number. Now we shall look at such examples as we move on. Now let's turn to oxidation on the other hand, which can be defined as addition of oxygen. If you add oxygen to a substance, you have oxidized it. For example, when you react copper 2 oxide with iron, like in the case we had just talked about before, you have added oxygen to iron to form iron 2 oxide. Therefore, iron has been oxidized. Then we have the loss of electrons. During chemical reactions, like we are going to see as we move on, you'll realize that in some reactions, electrons are lost, while in others, electrons are gained. So oxidation can be defined as the loss of electrons. It can also be defined as the loss of hydrogen. When hydrogen is removed from a substance, then that is oxidation, the loss of hydrogen. And then finally, oxidation can be defined as the increase in oxidation numbers. So when the oxidation number increases, then that also becomes oxidation. Now, some of these definitions may seem difficult to understand, but as we move on, you will be able to identify with them. Now, in terms of oxidation number, that is the definition of oxidation and reduction in terms of oxidation number. Then we say that oxidation is increase in oxidation numbers, while reduction is the decrease in oxidation numbers. In redox reactions, we shall be able to talk about oxidation and reduction mostly, because earlier on we said redox is simultaneous increase in the oxidation number of one species in a reaction and a decrease in the oxidation number of another species. That is what redox is all about. Both reduction and oxidation taking place at the same time in the same reaction. Now, the reducing agent is the species that undergoes oxidation. So that species which shows an increase in oxidation number is the one we call the reducing agent. Therefore, an increase in its oxidation number, yes, as I've said before, the species that at the end of the reaction will have an increased oxidation number, or a bigger oxidation number than it had in the reactant side, that is called the reducing agent. An oxidizing agent, on the other hand, is the species that undergoes reduction in oxidation number, whereby the oxidation number reduces at the end of the reaction. For example, it may start from a positive 2 to 0. So that one is an oxidizing agent. And in a redox reaction, there is an oxidizing agent and a reducing agent. So there is one substance which at the end of the reaction will end up reducing in oxidation number, and another which will end up in increasing in oxidation number. Let us now move on to calculation of oxidation numbers. Now, there are some guidelines that are applied in assigning oxidation numbers to different elements. So let's look at each one of the guidelines and look at examples. Now, rule number 1. Oxidation number of combined oxygen is always -2, except in peroxides such as sodium peroxide and hydrogen peroxide, as shown in this statement, where it is -1. So whenever you are assigning oxygen an oxidation number, it will always be equal to -2 when it is in a combined state, unless that particular compound is a peroxide and we only have 2 peroxides, that is sodium peroxide and hydrogen peroxide. That is the only case where we assign oxygen an oxidation number of -1. In all the other compounds, the oxidation number is -2. Now, rule number 2, or guideline number 2, the oxidation number of combined hydrogen is always +1. So whenever hydrogen is present in a compound, we assign it an oxidation number of +1, except in metal hydrides such as sodium hydride and potassium hydride, where the oxidation number is normally assigned as -1. Rule number 3. All atoms and molecules of elements have an oxidation number of 0. So whenever you have an atom or a molecule in a reaction, you will assign them oxidation number 0. That is our rule number 3. Rule number 4. All combined metals and non-metals have oxidation numbers assigned equal to the oxidation state or valency. So, in other words, the oxidation numbers of metals and non-metals in the combined state is just equal to their valencies or their oxidation state. I hope that makes sense. All metals and non-metals which are in the combined state, we assign them an oxidation number equivalent to their valency or equivalent to their oxidation state. Rule number 5. The sum of oxidation numbers of atoms of elements making a compound is always equal to 0. For example, if you have a compound like magnesium oxide, the sum of all the oxidation numbers in magnesium and oxygen should be equal to 0. Now, rule number 6. The sum of the oxidation numbers of atoms of elements making a charged radical is equal to its charge. For example, a radical like sulfate, it is an SO4 2 negative. So the sum of all the oxidation numbers present there and the atoms present are sulfur and 4 oxygens. The sum of those oxidation numbers should be equal to -2, which is the charge on the radical. Now, using this rule, the oxidation number of an unknown atom of an element in a charged radical or a complex ion can be determined as shown in the example below. Now, you are told calculate the oxidation number of the elements in bracket, and you are given nitrogen 2 oxide. Now, you are required to find the oxidation number of nitrogen in this particular case. Now, what you do, you let the oxidation number of nitrogen be equal to a letter X, such that when you go back to NO, we know the oxidation number of oxygen is always -2 except in peroxide and hydrogen peroxide. No, except in peroxide. Now, look at this is not a peroxide. So the oxidation number of oxygen here is -2. So we shall just take X, that is the oxidation number of nitrogen, which we do not know, plus -2. -2, which is the oxidation number of oxygen. And because it's only one atom, then the total should be equal to the overall charge of the compound, which is 0. It doesn't have any charge. So we can say the overall charge is 0. Then mathematically, we shall be able to leave X on that side and move -2 to the other side of the equation, of the equal sign, such that it becomes +2. Therefore, the oxidation number of nitrogen in nitrogen 2 oxide is +2. Another example, NO2. Find the oxidation state of nitrogen in nitrogen 4 oxide, which is NO2. Now again, we shall let the oxidation number of nitrogen be equal to X, such that we shall say X plus. Now, in this case, the oxygens are 2. So we shall put 2 into the oxidation number of oxygen. this is not a peroxide again. Therefore, the oxidation number of oxygen will remain -2. So 2 times -2 should be equal to 0. So X plus -4 should be equal to 0. So our X will be equal to, move -4 to the other side of the equal sign, and it becomes +4. So our X, which is the oxidation number of nitrogen, is +4. Another example. Find the oxidation number of nitrogen in ammonia gas. So again, let N be equal to X. Let the oxidation number of N be equal to X. So that you'll have X plus hydrogens are 3. So 3 times the oxidation number of hydrogen, which is +1, should be equal to 0. From there, we work it out mathematically. X plus 3 should be equal to 0. Move 3 to the other side of the equal sign, it shall be -3. So the oxidation number of nitrogen in ammonia gas is equal to -3. By now, I hope you have noted that some of these elements do not have a constant oxidation number. It varies from compound to compound. In one compound, it can be -2. In the other compound, it can be -3. In another, it can even be -1, and so on and so forth. So that is the case of nitrogen in different compounds. Now, attempt the following exercise as you try to revise and evaluate yourself on whether you are able to calculate the oxidation numbers of elements. So in this case, we are finding the oxidation number of the element in brackets, and the last number there is supposed to be the power. It is supposed to be the power. So attempt those questions. See whether you are able to find the correct oxidation state. Displacement of metals from their solutions. Let us look at how metals are displaced from their solutions. Now, displacement reactions are redox reactions, whereby the more reactive metal displaces the less reactive metal from the solution. I gave you an example of iron metal and copper 2 sulfate solution. Now, whenever you put iron metal in a solution of copper 2 sulfate, then the iron displaces copper from its solution. Therefore, the products will be iron 2 sulfate plus copper. The reason this happens is because iron is more reactive than copper in the reactivity series. It is higher there than copper. Therefore, it has the ability to displace copper from its solution. So that is an example of a displacement reaction, which is a redox reaction. Now we shall see why we call it a redox reaction. So in that equation, we have copper 2 sulfate plus iron to give us iron 2 sulfate plus copper. Now we call it a redox reaction because if you look at the ionic equation corresponding to that reaction, we have copper ions as the ions that take part in the reaction from copper 2 sulfate, reacting with iron solid, the iron filings or the iron powder, to give us iron 2 ions plus copper, which is a solid. In other words, in the final product, we shall have a solution which is colorless of iron 2 sulfate, whereby the iron 2 ions are the main product, and copper solid, a brown deposit, will be deposited at the bottom of the beaker. Now, we call it a redox reaction because the oxidation number of copper in copper 2 ions is 2 plus, or plus 2 is plus 2. On the product, it is now copper metal being produced, whose oxidation number is 0. Therefore, there is a decrease in oxidation number from positive 2 to 0. Thus, an oxidation has happened. Yes, then on the other hand, we have the oxidation number of iron moving from 0 to positive 2. 0 in the iron solid and positive 2 in the iron 2 ions. Thus, that is an increase in oxidation number, and we call it oxidation. The more reactive metal, which is iron, undergoes oxidation, which is the reducing agent. So iron is a reducing agent by losing electrons to form positively charged ions. Then the less reactive metal, that is copper, undergoes reduction, and we call it the oxidizing agent in solution by gaining electrons. Generally, we can say that displacement of metals involves electron transfer from a more reactive metal to another less reactive metal. Now let's look at some more examples of redox reactions. Now look at the equation of reacting iron with zinc. Ionically, we have iron 2 ions in solution plus zinc solid, forming zinc ions plus iron solid. Now this happens because zinc is more reactive than iron. Therefore, it displaces iron from solution, and then it forms zinc sulfate or just zinc ions in a solution and iron solid. Looking at the two, we have the oxidation number of iron reducing from positive 2 to 0. So that is reduction. And the oxidation number of zinc increasing from 0 to positive 2. That is oxidation. Therefore, iron, which gains electrons, is the oxidizing agent. On the other hand, zinc loses electrons to form zinc ions. It is oxidized as its oxidation number increases from 0 to positive 2, and therefore it is the reducing agent. We have iron 2 ions reacting with magnesium solid to form magnesium ions and iron solid. So iron 2 ions are the ones which are reduced, while magnesium is oxidized, because we can see there is an increase in oxidation number. Look at copper ions reacting with zinc. Zinc, being more reactive than copper, displaces copper from solution to form copper solid and zinc ions. So copper oxidation number decreases from positive 2 to 0. Therefore, it has undergone reduction, while zinc, the oxidation number increases from 0 to positive 2. Therefore, it undergoes oxidation. Now, let's note the following. The number of electrons donated or lost must be equal to the number of electrons gained or acquired. Therefore, if, for example, in the above equation of copper 2 ions and zinc, copper gains 2 electrons, that number of electrons gained by copper should be the number of electrons lost by zinc. So when balancing our charges, we should take care of that. Another point to note is that during displacement reactions, the color of ions or salts may fade or may not fade. And if it does not fade, it does not mean that displacement has not taken place. No. So whether it fades or does not fade, then displacement has taken place. For example, in the reaction between iron 2 ions and magnesium, Now, ion 2 ions are usually green in solution. So the green color of ion 2 ions fades because ion 2 ions are displaced from the solution. So that is an example of a reaction whereby the color fades. So ion 2 ions will involve a color fading. Initially it would be green in color, but as the displacement takes place, it would fade away. The green color will fade off. And also, in the reaction between copper 2 ions and zinc solid, to form zinc ions and copper solid, then the blue color of copper 2 ions fades, and this is because copper ions are displaced from the solution and a brown solid is deposited. So in the beaker you will see a browny deposit at the bottom, and that is when copper metal is formed. It is deposited at the bottom of the beaker, and therefore you will be able to notice a brown deposit. Other redox reactions include reacting ion 2 chloride with chlorine gas to form ion 3 chloride. The green ion 2 are oxidized to yellow ion 3 ions. Oxidation state increases from positive 2 to positive 3, while chlorine gas is reduced from 0 to -1. So that is also a reaction that involves redox. Another equation is when hydrogen sulfide reacts with sulfur 4 oxide to form sulfur and water. So in this case, hydrogen sulfide is the reducing agent as the oxidation number of sulfur increases from -2 to 0, while sulfur 4 oxide gas is the oxidizing agent as the oxidation number of sulfur in sulfur 4 oxide decreases from +4 to 0.